All right, so we're now taking a look at learning targets 3 and 5. It's going to follow the notes from Glencoe 12.5 and 12.8. All right, so our very first example, Keisha has a stack of 8 baseball cards, 5 basketball cards, and 6 soccer cards. If she selects a card at random from the stack, what is the probability that it is a baseball or a soccer card? All right, well, the first thing to point out, we have the word or. Or means we're going to have a probability plus another probability, okay? Now, the thing we have to be careful of whenever we're adding probabilities is whether or not they're mutually exclusive. Now, these two, according to the title, are mutually exclusive. The reason being is because you can't have a card that is both baseball and soccer. If there was a card that existed that was both baseball and soccer, then we would subtract away the probability so that as to not count it twice, okay? So the first probability we're dealing with is what is the probability of drawing a baseball card? Well, there are 8 baseball cards out of a total of 19 cards. And I got 19 by adding 8, 5, and 6, the total number of cards provided in the problem. The next question, or the next part of the problem is soccer card. Well, the probability of drawing a soccer card is 6 out of 19. And when I add these two probabilities together, I get the probability of 14 out of 19. So I have some pretty good odds here. All right, let's look at our next problem where we have 3 mutually exclusive events. Got a little bit of an error here. There are 7 girls and 6 boys in the junior homecoming committee. A subcommittee of 4 people are being chosen at random to decide the theme for the class float. What's the probability that we'll have at least 2 girls on this committee? I'm zooming out because I'm going to need some space on this one. First off, I don't know the number of ways people can be chosen. So I actually don't know the arrangements for these people. For example, me having Miss Rudolph, Miss Walker, and Miss Sutton helping out is different from Miss Sutton and Miss Bilkey and Mr. DeWitt helping out. And there's a lot of different ways that these people can be arranged. Now, what I'm hinting at is the fact that I'm going to have to use combinations in this problem here. Now, the other thing we have to worry about is the probability of at least 2 girls. This means that I could have 2 girls, or, which means add, I could have 3 girls. But I'm still not done because, or I could have 4 girls. Notice how this problem started off as just, oh, the probability of at least this many people happening. But it actually just turned into an even bigger problem. Now, the other thing we have to recognize is when I have 2 girls, then I'm automatically going to have 2 boys, okay? Because in total, I'm choosing 4 people. If I have 3 girls, then I have to have 1 boy. And if there are 4 girls, I will not have any boys. So I actually don't even need to worry about that there. Now, the total number, so it's always specific over total. The total number for all of these probabilities will be the exact same, okay? So in total, I have 7 girls and 6 boys, so I have 13 children, and I'm going to choose 4 of them. 13 kids, and I'm choosing 4 of them in all of these situations here. Now, if it's 2 girls and 2 boys, that means I'm going to multiply the number of girls and the number of boys. So we're going to have 7 girls, and we're choosing 2 of them, multiplied by, we have 6 boys, and we're choosing 2 of them, okay? Notice we have girls and boys, that's why we multiply. Here we have 7 girls, and I'm choosing 3 of them, multiplied by the 6 boys, and I'm choosing 1 of them. Lastly, we have 7 girls, and we are choosing 4 of them. And the reason we don't worry about choosing 0 boys is because there's only one way to choose nothing, and so it wouldn't affect our answer here. All right, so now, got to do a little calculations. This first probability here, if we type this in and we calculate, we get 315 over 715. Next probability, if we type that in and calculate it, we get 210 over 715. And the very last one, we get 35 over 715. We add them all up, and we do not need to subtract anything because none of them will overlap with one another. We get approximately, if we simplify our fraction, 112 over 143. So it's about a 78% chance of this occurring. All right, in the last example for this section, we have what's called inclusive events. Another way of saying inclusive events is actually saying non-mutually exclusive, aka things that can occur at the same time. So non-mutually exclusive, okay? So in this problem here, we have enrollment at this high school. It's 1,400 students. 550 of them are taking French, 700 are in algebra, and 400 are in both French and algebra. What is the probability that a student at random selected takes French or algebra? So we first are going to have to recognize that's going to be the probability of French plus the probability of algebra. And in this scenario, because something can happen at both times, we have 400 kids who take both classes, we have to subtract them. The reason we have to do this is because of the fact that, let's say I have little Timmy. Let's say Timmy is counted in the French group and the algebra group. That means he was counted twice, but he's only one person, so he should actually be only counted once. All right. And a little thing I want to point out here is I just use some fancy notation. This is the symbol for intersection where I have both French and algebra, okay? So the probability that I have French students is 550 out of the total number of 1,400. I'm going to add my number of algebra kiddos, so 700 over 1,400. And we're going to subtract our overlap of 400 over 1,400. So 550 plus 700 minus 400 is going to get me a smaller numerator. And then if I add all of these things up together, it'll simplify to being 17 over 28. All right, continuing, we're now going to move into our very last section, and you're going to notice that I'm actually going to solve all these problems slightly different than your textbook does, okay? So your textbook will use what's called the binomial theorem, and I'm actually not teaching that this semester. It's something you'll look into in pre-calculus, okay? So if a family has 4 children, what is the probability that they have 3 girls and 1 boy? Important fact to remember, with probability, we're still going to do the specific divided by the total, okay? Now let's think about the total first off. We're going to have 4 children, okay, and we only have 2 possibilities for each of them, boy or girl, boy or girl, boy or girl, boy or girl. When we multiply them together by the fundamental counting principle, that gets us 16 possibilities, okay? Now the specific. One of the ways that I like to treat these is like they're Mississippi cases, okay? So here we go. Mississippi case, I want 3 boys, so I'm going to give myself 3 letter B's and 1 letter G. Pretend this is a word. This is a Mississippi case because we have repetition. We have the letter B repeating ourselves. So this is going to be the total number of letters, which is 4, divided by our repeat offenders, which is the letter B repeating himself 3 times. So then this is going to simplify to being 4. So then we put 4 over 16, which will simplify to 1/4. So I have a 25% chance of this occurring. Now let's talk about how your book actually does approach them, okay? Your book uses a formula that is just produced by the binomial theorem. So what you would just need to recognize is the fact that we have 4 children and we're going to choose, let's do 3 boys. We'll focus our efforts there, okay? Now the first probability we're dealing with is boys. We have a 50% chance of it being a boy, and we want to have 3 boys, okay? And then we also have a 50% chance of having girls, but we only need 1 girl. This expression right here actually produces the same thing as what we just did over here, where we have the specific event that we want to have happen, the number of ways this could happen, multiplied by the probabilities of what we want and the opposite, the failures essentially. So let's actually use this strategy when solving our next hockey problem, okay? So the question reads that we have a hockey star, Jaromir Jagr. He takes a shot and he has 1/7 the probability of scoring a goal. He takes 6 shots in a game one night, okay? So we're dealing with, first off, the probability of scoring exactly 2 goals here, okay? So exactly 2 goals. So that means that we're going to have 6 shots, and we're choosing 2 of them to be goals, okay? This is the number of ways for this to occur. we're going to multiply this by the probability of scoring a goal and the probability of missing a goal, and the number of ways that each thing occurs. So the probability that I score a goal is 1/7, okay? And I want this to happen twice, so I raise it to the second power. Now the complement of this event happening, so its opposite, is 6/7, okay? And I'm going to miss my shots 4 times. So I'm going to raise that to the 4th power, okay? When I type in this lovely expression here, I get a really hideous number, but that's okay. Ugly numbers will happen, especially in probability. 19,440 over 117,649, which is approximately 17%, okay? All right, so this last example, we're dealing with scoring at least 2 goals. Now, it's important to recognize that at least 2 goals means that I can score 2 goals, or 3 goals, or 4 goals, or 5 goals, or 6 goals. That's all the probabilities I would need to find. Rather than doing that, I'm actually going to use the complement, okay? So I'm going to find the probability of that not happening, and then I'm just going to subtract that from 100%, okay? Now, this not occurring, so I have 100%, I'm going to subtract away the probability of scoring no goals, and I'm also going to subtract away this probability of scoring 1 goal, because those are the 2 scenarios that do not complete the at least 2 goal option. Now, scoring 0 goals. The setup for this one, we have 6 choose 0, okay? Then this, the probability of scoring a goal was 1/7. We don't want that to occur, so it's to the 0th power. Now, the 6/7 is his complement, and that's going to be raised to the 6th power, because this will be the probability of 0 goals. 1 goal. So now we have 6 shots, and we only want 1 of them to be a goal. So we're going to have 1/7 to the 1st power. Once again, this is the number of arrangements, the number of ways that this setup could occur, okay? And then we have the probability of occurring raised to the number of times we want that goal to happen. And it's being multiplied by 6/7 to the 5th power, because that'll complete that, okay? So once again, 100% minus these 2 probabilities here. So let's just change 100% into a decimal form of 1. And then 6 choose 0 times 1/7 to the 0 times 6/7 to the 6. That's approximately 46,656 over 117,649. We'll do the same thing here. Type that in and get our solution. Notice that they're actually the exact same value. And I want you to think about why that occurred. These 2 numbers are different. These numbers are different. Can you think about what algebraically caused this to happen? Well, this expression then ends up totally to be 24,337 all over 117,649, so approximately 21% chances of this occurring.